ANA Physics, it's Mr. Neff. Today, let's look at the steamy hot problem. You're going to calculate the mass of steam, which is initially at 130 degrees C, that you need to warm up 200 grams of water, which is initially at 20 degrees C, to 50 degrees C. So you're just so you can visualize the problem here, you're going to have a beaker of water, and there it is, and that is 200 grams of it, and it's at 20 degrees C. Now you're going to inject some steam into this. I'm going to draw that as red. So you're going to take, maybe you have some kind of hose that you can shoot the steam out of, and so you're going to put some steam into that. And I don't know how much mass you need. If you put in a little bit of steam, it's going to raise the temperature a little. If you put in a ton of steam, it's going to raise the temperature a lot. We want the perfect amount so that it gets to 50 degrees C. Now, that would be easy enough, but the other thing that you got to think about is the glass. And the glass is going to take in some of that heat as well. So some of the heat is going to go into the water and raise it, but some of the heat is going to go into the glass. I've given the 840 joule per kilogram per C degree specific heat of glass up here, and we're going to solve this. So now, what you want to think whenever you look at a problem like this is you want to think about the heat that is lost by the steam, and then the heat that is gained by both the glass and the water. Now, those two are equal in magnitude. Now, you have to be careful, though, because of the signs. Because the heat is lost, you're going to have some delta T's that are going to be negative, and over here, you're going to have delta T's that are going to be positive. Now, you've done enough of this to know that one of the ways that you calculate these is, especially the parts that the temperature actually changes, one of the ways you calculate these is you do the temperature change, MC delta T. Well, to handle that, you're going to do one of two things. You're either going to make those heat lost terms negative, or you're going to just add them all up and make them equal to zero, or you're going to say higher temperature minus lower temperature rather than doing final minus initial for deltas the way you usually do it. So it's going to be like, the way I'm going to do it this way is I'm going to say that the heat lost by the steam is the heat gained by the glass and the water. And I'm going to show that on two graphs. So this is going to be that temperature versus heat graph. And we are familiar with this. That's going to be the one for the water. And then I'm also going to have the one for the glass. The one for the glass, we have solid glass, frozen glass. And so glass would be something like this. It's supposed to be straight. That would be something like this. And I don't really need, I'm not going to start melting the glass. We don't have that kind of heat. So here it is. So now what I'd like you to do is I'd like you to stop the video, and I'd like you to show the 5 heats associated with this. The 3 of them are going to be the heats that are lost by the water, and 2 of them are going to be the heats that are gained by the glass, and one from the glass and one from the water. So stop the video and try to mark those on the graphs. Okay, we're back. So you know that the water starts off in a liquid form, and that's going to be right around here. This right here is 0 degrees C. This right here is 100 degrees C. My scale's not awesome on this. The water's going to do this. The glass is going to do something like that too. The glass is going to start here, and maybe that's at 20 degrees C, and it's going to go up to 50 degrees C. And there's the heat that is going to be absorbed by the glass. Now the water, or the steam on the other hand, is going to do something similar but different. And so it's starting up here in the vapor area, so it's going to go down like this. Then there's going to be this long latent zone right here, and then it's fine. Once it gets down to 100, then it's finally going to meet the water in the middle. So let's name these. Let's call the ones from that are the gainers, let's call them heat 1 and heat 2. And then let's call the ones that are losses, let's call them heat 3, heat 4, and heat 5. All right, so now what I'd like you to do is I'd like you to stop the video, and I would like you to make an equation with all of those Q's, okay? All right, we're back. And so a couple ways this could be done. One way that I'm going to do this is I'm going to say Q1 plus Q2 is equal to Q3 plus Q4 plus Q5. Right, there they are. Now, you got to be careful here, though. You know, for the Q's, particularly the Q1, 2, 3, and 5. Not the 4, because that's one of the latents, but because those other ones have those delta T's in there. So Q1 is going to be the mass of the water times the specific heat of water times the delta T of the water. The Q2 is going to be the mass of the glass, specific heat of the glass, delta T of the glass. Now, those delta T's are both positive terms. No problem. Now, where you could run into a small problem is on the other side, with the Q3 is going to be the MC delta T. That C is the steam, water in the steam form, specific heat, which is like half, it's not half, but it's in the ballpark of half of the one for liquid water. And this M, of course, is our answer. This delta T, though, is going to be a negative term because we're going from 130 down to 100. So if I make that negative, and these other terms are going to be negative, I'm going to have a positive thing equals a negative thing. Well, you know deep down that doesn't work. So I'm not going to make this final minus initial for this delta T. I'm just going to make this higher temperature minus lower temperature to symbolize the amount of heat, the magnitude of heat. And not to say that it's a vector, because it's not, but the magnitude of the heat. And so that's going to be 30 C degrees eventually put into there. Now, for the latent part, it's going to be MLVs for latent heat of vaporization. And I'm going to make that positive as well. And then over here, I'm going to make this MC delta T. Now, careful. This C is for steam. This C is for water. That was the same as this C over here for water. Remember, the Q2 refers to the glass, so that one's for the glass. All right, how about this? Stop the video now and see if you can solve for these M. All three of those M's on the right side are the same. Let's see if we can solve for that M. All right, we're back. Now, I got a whole bunch of numbers here, but check out what I have. So I have a mass of the water times the specific heat of the water times the temperature change that the water did. I have the mass of the glass, the specific heat of the glass, and the temperature change that the glass did. When you put that into your machine, you end up getting an amount of joules, and it's a lot. It's 27,636 joules, and I bet you saw that. I'll put the unit here, even though I left all the units off up there. I thought it was going to get messy enough. On the other side, I have I factored out the M from each one of the terms, and so what's left is the specific heat of steam, which is 2010, times the 30-degree temperature difference. Now, again, I know that it went down in temperature, and so I know that you might be tempted to put a negative in for this. If you do put a negative in for this, then you probably also artificially put negatives in front of each one of the terms, which is fine. That's a technique they teach in chemistry. And that negative cancels out the negative. Me, I just did this as a magnitude of heat. Then here is the latent heat of vaporization of the water for water, and this is the specific heat of the water times the temperature change that it did. Now, when I multiply all of that out, I end up getting 2,529,000. And since the mass is going to be in kilograms, this is the rest of the joule. And so this is going to be meters square per second square. And so then when you go ahead and divide that out, you end up getting 0.0109 kilograms or 10.9 grams of steam. So what we did there, we figured out how much heat was lost by the steam, how much heat was gained by the other two. We set those equal as magnitudes of heat. And yeah, there were a lot of terms there. There were a lot of numbers there. But if we just took our time, carefully went through it, we should be able to get the right answer. I hope you did too. Try it again if you had difficulty.